Hello, everybody. Here is our review for the final. Make sure you get it done. You need to complete the whole thing to get the credit. All right, first things first, put your name here and your last initial, just like that. Super simple, right? All right, these first ones, I mean, you can very easily Google these things, right, and match the names, but if you want to know from me, let's see. Atoms contain negative particles called electrons. That was J.J. Thomson in the cathode ray tube experiment. Electrons move around the nucleus in specific fixed orbits. That is this very specific model that we have been using. This is called the Bohr model. We actually didn't talk about this guy. This is James Chadwick. I think I spelled his name right, but you know what? It doesn't matter. Don't write anything here. We're just going to leave this one out of it. All right, atoms contain a dense positive nucleus. This was the gold foil experiment where they shot particles and some of them bounced off. Most of them went through. Atoms are indivisible and resemble billiard balls. That was John Dalton, the father of modern atomic theory. All right, moving on. So here we're not going to do all of them, but I'm just going to give you the tools to figure out how to do this. Also, we'll look at our periodic table a little bit so we can make sure we remember certain things. So this first one is zinc 75 2 plus. We look at our periodic table here. Here's zinc, and we see that zinc is number 30. And something that we should remember from everything that we have done is that the atomic number and the number of protons is always the same. Always the same, no matter what. So here we said zinc was 30, so we'll put that in there, 30, and then we know the number of protons is also 30. All right. Now, sometimes they'll give it to you right here, but this larger number is always going to be the mass. The large number is always the mass. So right here is 65. Now, what if they don't give us the mass? How do we know it? Mass is always protons plus neutrons. Protons plus neutrons gives me mass. And then, conversely, they haven't given us neutrons, but we can use the same math. We can say mass minus protons gives me neutrons. Let's do that. 65 minus 30 gives me 35 neutrons. You can double check me in your calculator, but I think I am correct. All right, the next one is electrons. Electrons is going to be protons minus charge. And we want to be very careful with this one. I'll show you an example in just a second about how that can get kind of tricky. But in this case here, our protons are 30. I'll go ahead and write this when I have some space. So 30 minus, and then what is my charge? My charge here can be in a few different places, but that is where my charge is, positive 2. Now, if our charge is positive 2, that just means it's 2. So 30 minus 2, that's going to give me 28. So I know I have 28 electrons. Excellent. Now, let's move on. No, let me write this one down. So what would the charge be? If they didn't give us the charge, what would it be for this? It would be protons minus the number of electrons. Again, we're just using this same math here. Let's jump down. Let's try this one out. So right here, it doesn't give me the element or the atomic number, but it does give me the number of protons. And if I just do what I said I was going to do, right here, number of protons is 34. I can find number 34 is here. Se, that is selenium. So if the protons are 34, the atomic number is also 34. And we just said that the element was selenium. This is the mass. The large number always goes on top, and the smaller number always goes on bottom. There we go. Neutrons. We just said neutrons was mass minus protons. Let me get this out of the way. Mass minus protons. So let's take our mass of 74 minus our protons 34. 4 minus 4 is 0, and 7 minus 3 is 4. So that leaves us with 40 neutrons. Excellent. All right. Next part, number of electrons. Protons minus charge. So my number of protons is 34 minus my charge is 0. Now, some people were getting this incorrect because they were thinking if my charge is 0, my number of electrons is 0. That's incorrect. If your charge is 0, your number of electrons is equal to your number of protons. 34 minus 0 is 34. And then finally, we have valence electrons. Now, luckily, we should all remember that valence electrons are simple if you can just count columns. So here's my selenium, and I can count 1, 2, skip all these, 3, 4, 5, 6. Selenium has 6 valence electrons. Also, don't forget right there, 6A, 6 valence electrons. Okay, we're not going to do this whole one here. Phosphorus is, I'll just help you out. Phosphorus is number 15. You know what? We will do the whole thing. Phosphorus is number 15, so that means it's got 15 protons, 15 atomic number. Its neutrons would be 35 minus 15. You can double check your calculator, but that's going to be 20. The number of electrons is protons minus charge. All right, so this is the part, these two things here. Hold on. This is the part where it can get a little bit tricky. You have to be careful. So my number of protons is 15. So 15 minus charge. My charge is not 3. My charge is negative 3. So I have to make sure in my calculator it's 15 minus negative 3. And if I put that correctly, I'm going to get 18. Oops. 18. All right, and then valence electrons for phosphorus. Phosphorus is in group 5A, fifth column, 5 valence electrons. Go ahead and pause if you need to write that down. All right, on this part, it gives you the equation. And if you have any problems like this on your exam, the equation will be given to you. Let me get my calculator out here. All right, so in this equation, as we can see, we need to have a large fraction. I'm going to go ahead and make a fraction. I'm going to do alpha y equals, brings up this thing, and I'm just going to hit enter, and it says a fraction. Excellent. So the first thing in our equation, it tells us to put a parentheses, do the mass of the first isotope. Everything is laid out real straightforward. There's the mass of the first isotope, 34.00. And then my equation says times the percent abundance, times the percent abundance. Well, here's the percent abundance. It's right next to it. There's no guesswork here. So it's the mass times the percent abundance. And then my equation says plus the next one, mass times percent abundance. Doing this, 0.00 times 65.00, okay, plus the next one, 37 times 20, okay? And then I go down and I have to make sure to divide everything by 100. So here, oh, I forgot to put a times right there. Just goes to show anybody can make a mistake. Okay, there we go. Now I got it. And my answer is 35.25 for the first one. The second one works exactly the same way. You can do it, I'm sure. All right, here for definitions. Google's your best friend here, all right? The thing that we really needed to remember about isotopes and ions is what is it that we were changing about them? And so in isotopes, we were changing the number of neutrons. And that in turn changes the mass. And here, for ions, we were changing the number of electrons. You can always abbreviate electrons with the E minus. We changed electrons, and when we change electrons, that in turn changes the charge. We said this way back when. Now, these other things, I am 100% sure you could get them, find the definitions, and study those definitions. Now, what's the same about these? The number of protons, right? We only got three things: protons, neutrons, and electrons. Now, here, the electrons could also be the same, but it's not necessary. And here, the neutrons can also be the same. The only one thing is changing. All right, on this one, everything should be pretty easy to look up. Um, I'm going to be honest with you. I don't mind if you don't color. That's okay, but you do need to label things. For instance, here are my alkali metals, alkaline earth metals. These right here are my transition metals, halogens, and noble gases. So make sure you label all those. And then we said, I'm going to draw this off to the side. And then we said that we had some trends, like in this direction, like from this direction to this direction. In that direction, the size of the atom increases. And the ionization energy and the electronegativity are the opposite. They increase in that direction. So what that means is the largest atoms, if we look at our size here, the largest atoms are going to be over here and the smallest ones up here. And the atoms with the highest ionization energy are going to be up here, and the highest electronegativity are going to be up here. That's what those arrows are telling us. Let's see how we can use that in an actual question. So here it says, circle the atom with the larger radius. And then it gives us some options. So let's find these here on our periodic table. So we got Ra, let's see. We got, let's see, go red. We got Ra, N, Ne, X. So according to my trend here, the one that is largest will be the one that's furthest this way and furthest this way, right? To the left and down. So which one of these is furthest left and down? It's pretty obvious. It's going to be Ra, right? And that's how the other ones work as well. So which one will have the highest electronegativity on the next question here? That's which one will have the highest electronegativity. You find these elements, and then electronegativity is this direction. Sorry, my arrows are ugly. this direction. Not making it any better. I'm sorry. So whichever one is furthest up and to the right is going to be the one with the highest electronegativity. That's it. All right, now this part might be the one that is possibly hardest to remember. But your periodic table does have the electron configuration still there. That's the S's right there. Remember the p orbitals and the d orbitals that we have right there. So for instance, if I want to find the electron configuration of magnesium, this first one says magnesium. Well, here's magnesium. Remember, I said what we're doing is kind of like taking a census. Remember, like counting everybody that lives in all the streets, and magnesium is the last person that lives there. So we're going to start at the beginning. We're going to say 1S. 1S. And then how many people live in the first S house? Hydrogen and helium. That's 2 people. So that's 1S2. Right? And then on the second street, in the S house, how many people live there? Lithium and beryllium. So that's 2 people. And then also, we can't skip on the second street. In the P house, how many people live there? 1, 2, 3, 4, 5, 6 people live there. So 2p6. So 1s2, 2s2, 2p6. And then finally, on the third street in the S house, sodium and magnesium live there. And we were looking for magnesium. And so now we're done. That is the electron configuration of magnesium. And then we said, if we want to do the noble gas configuration, we said if we want to do the noble gas configuration, we can skip most of these steps, I'm sorry. All right, so again, we're trying to get the noble gas configuration for magnesium. Well, instead of doing 1s2, 2s2, 2p, all that all over again, we're going to skip the first couple of streets, and we're going to skip all the way to the last street. We're going to say we counted everybody up into one of these noble gases. These are the ones we have to use. Right? Wow, that was a horrible circle. One of these noble gases here. And since neon is the last noble gas that we went to, we're going to use neon. So we're going to put in a bracket, neon. Again, we're saying we're skipping all of this up until neon, and then after neon, 3rd Street, S house, 2 people live there. You're going to notice, hopefully, that the end will always be the same, 3s2, 3s2, because it's the same element. Now, if you're given the electron configuration, it's actually really easy to find. You can skip all this. Go to the end. 5s1. Where's that? 1, 2, 3, 4, 5s. Number 1. This one's Rb, rubidium. Very simple in that. Okay, orbital notation. This is what we had started with, and this was the top bunk, bottom bunk, and we had a few rules. Mostly like you would just find aluminum. Here's aluminum. Aluminum has 13 protons, and in this case, if it has 13 protons, it also has 13 electrons. Geez, I'm just not good at this today. 13 electrons. There we go. So we got to put 13 arrows here. We got to go in order. And remember our rules. So the first rule was, okay, here, we're going to go up first. We can't go to the next street. This is the second street. We can't go to the next street before we fill up the first street. So let's put another one there. Top bunk, bottom bunk. Okay, we're done with the first street. Let's go to the second street. So this is the second street, both of these. But we said we can't go to the next house until we fill up the first house. So we're going to fill up the first house. Good. So that's 4. We're down. We got to get to 13, remember? Okay, now we're in a house with 3 rooms. This is one house right here. And the next thing we said was they're not going to share a room if they don't have to. They don't like sharing a room. So everybody's going to get a top bunk, top bunk, top bunk. That's 1, 2, 3, 4, 5, 6, 7. I need to get to 13, so I got to keep going. And we can't go to the third street yet because the second street's not filled up. So we will come back. They will share a room. All right, that's 10 electrons. I got 3 more. 1, 2, and then finally 3. That is the orbital notation for aluminum. 1s2, 2s2, 2p6, 3s2, 3p. All right, properties of covalent bonds. Covalent bonds, covalent like as in covalent. That means this side, remember, this staircase, this side is our non-metals, and covalent bonds is a non-metal and a non-metal together. Any two things over here, plus hydrogen counts as well. All right, and then a few things we said. We said that non-metal, non-metal. We said that this is a sharing. That's what covalence means. Valence means the electrons on the outside, co meaning together. Polar covalent are unequal sharing because if it's unequal, they create positive and negative, which is what polar means. Non-polar is the opposite, so non-polar is going to be equal sharing. Polar covalent bonds slightly conduct electricity, and non-polar do not conduct electricity. Here we had Lewis dot structures. Remember, we needed to count valence electrons and all this stuff. These particular ones are really important, like these specific molecules. And so I'm not going to draw out each one, but you should be able to find them all and be able to draw them. Lewis dot structures are some of the most common things in chemistry. If you can't find that somewhere, you're not looking hard enough. All right, so hydrogen, each hydrogen has 1 valence electron. Remember, we bond them together. This is non-polar because hydrogen and hydrogen are the same thing, so neither will pull electrons more than the other. And this is linear. All right, oxygen, hydrogen, hydrogen. Oxygen has 6 valence electrons. Remember, we're just counting columns. Oxygen is right there. It has 6A, 6 valence electrons. So I got 1, 2, 3, 4, 5, 6. I'm planning ahead because I know that it's going to bond with hydrogen here. Connect those. Hydrogen has 1 valence electron. Connect those. All right, cool. Water is polar. How do we know that water is polar? Because oxygen and hydrogen are very far apart on the periodic table. Oxygen is very electronegative. That means it's pulling electrons towards itself in that direction. I'm sorry. Those lone pairs make water bent. You should just memorize this. Water's polar and water's bent. It's going to be important later too. I'm going to help us out here with the shapes. I think if you look up the shapes and see how they work, you're going to understand. This one's trigonal pyramid, and this one is tetrahedral. How could we know that? Because this is bonded to 3 things. That's trigonal. This one's bonded to 4 things. Remember, 4 is tetra. An ionic compound is formed between a metal and a non-metal. There's a complete transfer of their valence electrons. Now, ionic bonds do not conduct electricity unless they are in water. For instance, salt. Salt does not conduct electricity unless you throw it in water, then it conducts very well. Now here, technically what you're supposed to do is draw out each thing. Sodium has one valence electron, and chlorine has 1, 2, 3, 4, 5, 6, 7. Remember, they want 8. So sodium will give up its one valence electron there. Boom. And we're going to get Na plus and Cl minus, and that'll give us the NaCl. Name of this is sodium. Instead of chlorine, we said we were going to go with chloride, right? That's how all ionic compounds work with their names. Now, what's really important is just being able to do the bonding with the charges. For instance, potassium. Potassium's always going to be +1, and sulfur's always going to be -2. We know this because it says it on our periodic table. Right there, potassium is +1, and sulfur right here is -2. So we get the charges from our periodic table. And then we ask ourselves, is this number and this number the same number? No, it's not. Then we're going to do crisscross applesauce. If it was the same number, then they would just go away. So we're going to end up with K2, 1. And the name of this is potassium sulfide. We just changed the ending to IDE. Last one I'm going to help us with beryllium and nitrogen. So I got beryllium and nitrogen. Again, I'm getting these charges straight from the periodic table. Beryllium here is +2 charge. Nitrogen here is -3 charge. Are these numbers the same? No. Crisscross applesauce. Yes, I know how silly that sounds. It's like that, so you'll remember. And the name of this is beryllium nitride. Beryllium nitride. I still have those written on my board. All right, now we should be able to figure these ones out. Remember, ides, like this, ide means it's an element. So bromide, right? Eights, ATE, those are polyatomic ions. You need to look at the back of your periodic table. Find, for instance, nitrate. Nitrate is NO3 minus 1, and you got to use the charges that are there. These, we just went over them. I'm not going to spend too much time here. But remember, here is the center point. Anytime we have an arrow, that is our center point. This is the left side, and this is the right side, and the left side has to equal the right side. For instance, the left side here is 60 and 64. Together, that's going to be 124 grams. The right side has to equal the same. The right side needs to be 88 plus something. Now, in algebra, what do we do when we don't know what something is? We'll put x. 88 plus x has to equal 124. And so to solve that, we're going to say 124 minus 88 is equal to x. And I'll go ahead and let you figure that one out for yourself. All right, here is very similar to what we did in class, balancing and figuring out what type of reaction. So this one is a simple reaction. We know this because there's only 2 and 1 thing. So 2 things, here's my center point. 2 things become 1 thing. That has to be a synthesis reaction. And then how do I balance it? I've got sodium and chlorine. Got 1 sodium on this side, 1 sodium on this side. 2 chlorines on this side. Got 1 chlorine on this side. Okay. Now again, the mistake that most people are making here is thinking they can just change this number. No, this is just the count of how many things we have. If we want to change something, we got to put the numbers here, the coefficients, remember? So if I need 2 chlorines on this side, right? I need 2 chlorines. I need that to be a 2. So if I gotta find my chlorine, there it is. and I got to multiply it by 2. And then I got to be very careful. This also multiplies my sodium. So now I have 2 sodiums here, and I have 2 chlorines. Okay, my chlorines are balanced. I'm good there. So now I got 2 sodiums here, and I got 1 sodium here. How do I make that into 2? I got to find my sodium on this side. Here it is. And I got to multiply it here by 2. Now I got 2 sodiums here. So 2 sodiums, 2 chlorines, and put a 1 right there. That is my balanced chemical equation. All right. Don't forget when you're doing a combustion, this is a combustion reaction. Oh, gave that one away. That you're going to have carbon, hydrogen, and oxygen. But on this side, you're going to have 2 places with oxygen. Right? 1 right there and 1 right there. And the most common mistake when balancing a combustion reaction is that we forget to multiply these oxygens out. We end up with a weird number, and it doesn't work. I promise you, on the exam, on the test we're going to take, it will be pretty simple. Oh, I see I've made a mistake here. The other class did go into this, and we did not. This is a double replacement reaction. We'll talk more about double replacement reactions later. But a double replacement reaction is when 2 things switch places. So you can see calcium. Calcium is with nitrate here. And over here, potassium is with nitrate. Potassium is with carbonate here. And over here, calcium is with carbonate here. I'm not going to count that one against you, and we're not going to do that on the exam. All right, here we go. Activity series. Whoops. Okay. We're trying to look over here at our activity series. I wonder if I could. Sorry. That's better. Okay, so we're just saying like aluminum or calcium. So I'm going to find aluminum. There's my aluminum. I'm going to find calcium. Calcium. Okay, so which one is more active or more reactive? In my class, we said which one's a better dancer? And in this case, it's going to be calcium. If we look over here, determine if this reaction will occur. Well, what is a reaction? A reaction is if these 2 things switch places. Do these 2 things switch places? Now, a lot of people have still been getting confused about which to look for, which ones am I comparing. It's always the first thing. It's going to be that thing and the first thing here. Most of the time it's a metal. Sometimes it'll be hydrogen, but it's almost always a metal. So this person here, ClO3 and Cl2 and PO4, these are the ones that get to choose the dance partner, right? They are looking for the best dance partner. And these 2 over here, guys or gals, or however you like to do it. I'm a guy, so I'm just going to say these 2 guys, this guy and this guy and this guy, and so on, they're trying to get the dance partner, right? But this one, they get to choose. So who's the better dancer gets to end up with the dance partner. So this right here is gold, and this right here is potassium. Let's find those here. So here's potassium, and gold is so far down. Gold is way down there outside of the screen. So we know gold is like down here or something, right? So clearly potassium is the better dancer. K, that's K. So K is the better dancer. So ClO3 is going to stick with K. So will these 2 guys trade places? No, they won't. So that means no reaction will happen, right? Now, if we found that they will trade places, yes, then we would say, yes, a reaction would happen. And that's it. All right, from my class, we don't have to do this part down here. We're all good. And that's it. Make sure you have everything filled in. Make sure your Chromebook's ready for your final, and let me know if you have any questions. Good luck with it.